everyone. So today we continue with the last subtopic, which is about 4.7, application of motion, charged particle in B and E. B is magnetic field, E is electric field. Okay. The two main applications are velocity selector and mass spectrometer. So this is an example of mass spectrometer. This is the velocity selector. So velocity selector, by its name, I think you guys can guess. The main application is to select the charge with a specific velocity. Okay, so you know that the charge might have a slightly different velocity. If you want to select just one particular velocity, just use velocity selector. The mass spectrometer normally used to identify the type of charge. Okay, example over here. So basically this is a velocity selector. How does it works? Normally if you have a charge that is moving into a magnetic field, this one is the magnetic field, it will start to experience a force. Like that one is what we call magnetic force. So in this example, let's say if my charge is sitting in the middle there, okay, and I have a positive charge, and the direction of velocity initially is to the right, so put to the right like that. So if you want to determine the direction of force, you can use the right hand rule, or right hand Fleming rule. Your thumb is pointing to the right, all your fingers is pointing out of the page, because the magnetic field is out of the page. And you can see that the force will be directed downwards. So this force is what we call FB, due to the magnetic field. Okay, and because you have a positive and negative here, right? So you guys know from chapter 1, electrostatic, if you have a negative terminal over here, it will produce a attractive force between the charge and the negative terminal there. So because the charge is positive, right? So in that direction, you have a force, what we call electric force. If, let's say, FE and FB are balanced, means that the magnitudes are equal, that means this charge will start to move in one direction, to the right, straight to the right. Okay, and normally over here, they will put a small slit. So that means if you have a little bit of deflections, let's say FE and FB are not balanced, then we start to move in that direction. So as a result, it will hit the slit and then it doesn't came out. So you only have one particular velocity of charge when it goes out over here. That's why this is what we call the velocity selector. So it selects the velocity. Okay, any other velocity, it start to move or deflected and it doesn't came out over here. Oops. In terms of workings, if the force are balanced, so I can say that force of electric field is equals to force of magnetic field. Okay, so this one, I mean, you have negative and positive terminal, so it will produce an electric field, and then that's why you have the charge moving in certain direction, right? So because of that, FB is equals to QVB sine theta. This one you learn in this topic. Theta here is 90 degrees because you can see that velocity is to the right, magnetic field is upward, so it's 90 degrees perpendicular to each other. And then over here, from chapter 1, F is equals to QE. Now I can cancel out the charge, and sine 90 is basically equals to 1. Therefore my V, velocity, is equals to E over B. Okay, so again, this is the drawings. Let's say if you have non-equivalent E and B, FB and FE is not the same, we start to deflect maybe in that direction or in that direction. Okay, if FE is bigger, that means the velocity is a bit too slow, so FB is a bit less, then it will start to deflect in that direction. If it is moving too fast, so V is bigger, so it start to deflect in FB direction. Okay. Okay, so another main application that you guys need to know is about mass spectrometer. Okay, mass spectrometer basically consists of two parts. Okay, the first part here is that this one is basically a velocity selector. So this one is continued from previously lah. Excuse me. And then this part is basically start to move in circular motion. Okay, and then over here you have a detector. Okay, this detector will be connected to a analysis tools like a computer or something, and they can create a graph or something. Okay, so this velocity selector, exactly like previously, you can see that there's a slit over there, and then you can select one particular velocity. So basically you know exactly how fast the charge is moving in this particular after it goes out from the velocity selector. Okay, example over here. Again, if you have a positive charge, just put it over there. So it goes to a velocity selector. You can select one particular velocity and goes out over here, and then it starts to experience only magnetic field. Okay, so over here you have magnetic field and electric field, but over here you only have magnetic field. So that one's positive charge. The direction of velocity initially to the right, B is going upwards, so you can see that the force is actually in this direction, downwards lah, over there, and it start to bend, and over here the force will be in that direction. Okay, this creates a circular motion. Okay, so how does it works in terms of the calculations? Okay, previously we know that the velocity that goes out over there is equals to E over B. V is equals to E over B. So if they have a different magnetic field value, maybe I have to put this one as B1, oops, and B2. Okay, so if I put B1 and B2, basically for velocity selector, it uses a B1. Okay, and then during the circular motion there, the equation that we can use is FB equals to FC. I mean, initially, if you want to use, if you want to write in terms of circular motion force, so FC equals to mv squared over r. FC equals to MAC over, MAC, and then AC is equals to V squared over R. So in sum of all forces to the center. So here, if I substitute force over here, it will be FB, because that's the only force that is experienced by the charge. FB is equals to QVB sine theta equals to 1. Okay, I can cancel out one of the V, and then if I want to write in terms of Q over M, this is basically charge per meter. This will be equals to V over RB. Okay, if you don't have the values for V, so basically you have to substitute this value inside here, right? So I just substitute inside here. So this V is basically the velocity that the charge came out from this part, from the velocity selector. Okay, remember that one more thing, one more important thing is that for the circular motion over here, the B is B2. Okay, but the V that you want to substitute there is basically B1. So I have E over R B1 B2. Okay, if the values of magnetic fields are the same, then this one becomes B squared. So normally they might ask you to calculate this part, or they might ask you to calculate the radius. So it depends on the questions. Okay, so this is the explanation. All atoms reaching the second magnetic field will have the same speed. Their radius of curvature will depend on their masses. So if you have a different mass, you have a slightly different curve. So that's why it hits a different region. So that's why you can identify a particle using the mass spectrometer. Okay, let's try to look at one of the examples. This one is from the tutorial question number 15. Question A says that sketch a diagram to show the structure of velocity selector in Bainbridge mass spectrometer. So this one, I can skip this part because we literally just discussed this part. Here for question B, in a mass spectrometer, a singly ionized molecule moves at a speed of 7.6 times 10 to the power of 13 meter per second on a circular path, has a radius of 15 centimeter. Okay, so they give you the velocity, the speed, and then the radius. And it says that the spectrometer uses the magnetic field of 0.15. Okay, so if I want to write the equations, if I want the question want to calculate the mass, right? So we are talking about the mass spectrometer region, which is when it starts to move in circular motion, like over here. Okay, so we know that I can write down Fc equals to mv squared over r. So basically this is the same with the previous derivation, where Fc is equals to Fb. Okay, and then I can substitute Fb with QVB. Okay, but since they already give you the velocity, we can straight away calculate over here. So mass is equals to QBR over V. Okay, I just rearrange it. Okay, it says here it's a singly ionized molecules. It means that you have one charge. I mean the charge is 1E. So it doesn't matter whether it's positive or negative. I just put this one as 1.6 times 10 to the power of negative 19. Magnetic field here is 0.15. Radius 0.15 as well. I change to meter. The velocity 7.6 times 10 to the power of 3. Okay, now you just have to calculate the values there, then you can get the values for mass. So if you press the calculator, you should get 4.74 times 10 to the power of negative 25, and the unit will be in kilogram as our unit. Okay, thank you everyone.